Hi guys, and welcome to another technical tutorial. In this edition, we're going to look at a puzzle that I recently faced, which was how to examine REST HTTP traffic. Well, that doesn't sound like much of a puzzle. You bring up a browser, for example. Here, you make REST requests to BPM, and you can switch on REST-based tracing in your browser. For example, I hit Control-Shift-I, and now I can come along and make a BPM REST request. Let's see, make a BPM REST request like this one, for example. Let's do a simple REST request, for example, what shall I do? This one, retrieve system details, execute the call, and look at the network traffic, and we can see in the trace the API that was made. Here's the API call that was made, and here's the response coming back from that BPM REST request. That's very simple, very easy, very straightforward, and we do this by examining the browser requests. But what if your REST request is not being made by a browser? What if your REST request is being made by an application, for example, a servlet or a Java EE application, or some other piece of technology which is not a browser? What if it's Node.js, for example, that's making the REST request? How can we examine the REST traffic to see what is going on? Well, this was the puzzle I faced. I'm not even going to bore you with the story behind it, but it was a puzzle I faced, and I encountered the great tool called Wireshark. Now, Wireshark is one of those open source applications where you can Google on Wireshark, go to its website, download it, install it, and you can go for it. Now, what Wireshark does is it traces network traffic. So, for example, if I start Wireshark, here's Wireshark, and I start recording, and we're now recording through Wireshark, and we can see there's traffic going on all over the place. So if I go and browse a couple of websites, and then stop Wireshark recording, we can come in here and we can see all of the traffic which Wireshark recorded on my network. Well, it's very low level stuff, but in here we'll find all of the traffic that was being sent, and it's network traffic, and it's low-level network traffic. And what I mean by this, it's the packets, the TCP packets that were being sent and received on the wire. Very, very low-level stuff. Okay, well, if I had to, I guess I could use Wireshark to record my HTTP traffic and then go grunge through it, but that's not very nice. But it would work. Unfortunately, it won't work, and the reason for this is that the HTTP traffic I'm working with is sent over HTTPS, otherwise known as TLS security or SSL security. Basically, the data being sent to the target servers is encrypted. And if I looked at the traffic that was going on, for example, port 80, let's see, TCP port equals 80. If we looked at the raw traffic, oh, it's not 80, it's 43 for SSL. If I looked at that traffic and looked at the application data, we would find that it is encrypted over TLS. And if we looked at the binary data that's being sent, we would find that it is completely meaningless. It's gibberish. You cannot examine network traffic and see the SSL content within it. So, gosh, well, is that the end of the story? Thankfully, no. There is another story that we can apply here. And that's where this comes into the picture. I'm going to pause for a second while I find my picture. There we go. This is what I wanted. So what we're seeing here is a transactional trace between a browser and a web server. Now, when we use SSL or TLS security. The browser says to the server, hello, and the server says hello back and returns with it the server's public certificate. The browser then generates a random key which it encrypts using the public key from the received web server. That then gets sent to the web server. Now both the server and the browser both have a unique key. The server comes back and says, okay, we're good. And then that unique key is then passed backwards and forwards, or not passed backwards and forwards. Data is then encrypted using that unique key and passed backwards and forwards. So can we have Wireshark decrypt our data for us? And the answer is yes. If we tell Wireshark about the key known to the web server, then Wireshark can examine the trace of packets and decrypt our data for us. Now, that is actually very easy to do. So let's go have a look at how we set up Wireshark to do this. File, and then we go, edit, and then preferences, and then protocols, and then SSL as the protocol we are configuring here. SSL, here we go. And in the configuration, we specify the key file that WebSphere application server is using in order to perform its encryption. This is the private key file to the WebSphere application server. Obviously, you don't want to be tracing SSL packets on your production systems, but on your development environment, that's fine. So we say we want to decrypt any incoming IP address that is targeting 9443, which is where WebSphere application server is listening on. We want to treat that data contained in that transport as though it was HTTP protocol. We point to the key store file, and then we supply WebAS, which is the default password for WebSphere application server. We also specify a secret keylog file, and we'll come back to this again in a moment. This is a file where keylog activity can be read from, and we'll come back to that in a moment. But with this set up, we can now go ahead and run our browser, and we can say I'm going to start recording. So let me log out of this and say start recording. Clear this filter, start recording. Record this under Wireshark, and go over to my browser and log in my browser. Let me log in using my user ID and password. Great. Now let's go and run a BPM REST API, and we will run one of the ones that we ran a few moments ago. We will retrieve this. We will execute the guest call. Done. Now let's stop recording, and we have here all of our trace. Now let's filter this just by HTTP. And now, by filtering on HTTP traffic, what we're actually seeing here is the SSL decoded traffic as sent between the browser and the BPM server. Here, for example, is my request to execute a BPM request. And if we look at how Wireshark has decoded it, it's decoded it as a physical frame which contains IP protocol, which contains TCP protocol, which was encrypted using SSL, and also here we see the magic, which once it's been decrypted, we see the underlying HTTP request that was sent over the wire. Now what this means is we can examine the requests and responses sent over the network between any two endpoints in our story. It doesn't have to be between the browser and BPM. It can be between an application and BPM. And that works just great. That works absolutely perfectly. So what this allows me to do is trace my network protocols between anything to BPM and anything from BPM, even though it is encrypted using SSL encryption. Now, in order for this story to work, it means that the initial exchange between the client application program and the BPM server has to be recorded, because it's during that initial exchange that the special key that is generated for this session is created. If we start tracing SSL communication later on, after the exchange of keys has occurred, then we won't have enough information in order to do the decryption. So if we're SSL tracing using Wireshark, be sure and start your SSL tracing before the initial exchange of keys. If you happen to be using browsers, then you can record that exchange of keys by setting an environment variable called, I forget what it's called. Oh, let me look at my environment variables. env pipe grep SSL. The environment variable is called SSL keylog file. If you start a Chrome browser with this environment variable in effect, then when Chrome runs, Chrome will log all of its negotiated private keys to this file, and those keys can then be examined by, or historically, by a instance of Wireshark, and that was the file that I specified here. So should we start Wireshark after initial protocol negotiations, we can tell Wireshark, go look in this file, which is then written to by Chrome and other browsers. Go look in here to see if you can find the corresponding one. But we only need that if our tracing doesn't initially include the key that is negotiated. All right, so lots of words here. Let me bring this to a conclusion. Wireshark is an open source tool. Wireshark can be used on both Linux and Windows to sniff the packets that are arriving at BPM or being sent by BPM. When we're tracing those packets, we're seeing them at the raw protocol levels. Because we're typically sending TLS encrypted data, we have to set up TLS property parameters. Those TLS property parameters specifically include pointing to the private key file that is used by the WebSphere application server to encrypt and decrypt packets. That is protected by a password, which by default is WebAS. We can tell Wireshark that any protocol arriving on or being sent from port 9443 is SSL protocol, and that using this we can decrypt that SSL protocol and treat it as HTTP protocol. From then on, TLS protocol seen over port 9443 can be decrypted as though it was HTTP, and then we can go into the HTTP packets and see what was physically sent on the wire TLS level and then decrypted using Wireshark using the keys. And we can see, without having to involve a browser, all the interactions. So what this allows us to do is do debugging at the BPM level where we don't have access to the initial requests. So for example, if we wanted to debug multiple HTTP REST requests arriving at BPM and we didn't have access to the browser's debug logs, we can sniff the traffic here. And this also becomes very useful if the interactions between BPM and its partner are REST, over HTTPS, where the two partners, one is BPM and the other is itself an application like Node.js. I hope you found something useful in this. If you've got any questions, feel free to post them, and I look forward to more of these in the future. Thanks, guys, and bye for now.